So what we have here in example 8 is a distillation column where we want the bottom of our distillation column to have an outlet stream of 100 kilomoles per hour, which is mostly carbon tetrachloride and partially carbon disulfide. And we know the feed stream conditions, and we have a specification of 2% of that carbon tetrachloride entering the column is supposed to be contained in the overhead stream leaving the column. So let's start with part A and draw our column out. So it's gonna look something like this. Draw your column real tall. We have an endless stream with a certain molar flow rate that we don't know, and it's 84% carbon tetrachloride and 16% carbon disulfide. And then we have a stream coming off the top of our column and a stream coming off the bottom of our column. And the stream coming off the top is N2. And that has some composition of carbon tetrachloride and carbon disulfide. And then our specification is that we have 100 kilomoles per hour coming off the bottom, and that's 97% carbon tetrachloride and 3% carbon disulfide. And our degree of freedom analysis is going to look like this, where we have 3 unknowns. So that's N1, N2, and X. 2 balances. So that's the carbon tetrachloride and carbon disulfide. And we have 1 additional info, and that is that we have 2% of this carbon tetrachloride that enters the column is coming out in the overhead stream. So that's something we can use later on. So in part B, it asks us to calculate the mass and mole fractions of CCl4 in the overhead stream and determine the molar flow rates of CCl4 and CS2 in the overhead and the feed streams. So let's start with that. So our total mass balance, or our total balance, is going to look like N1 is equal to N2 plus 100. And then our CCl4 balance is going to look like 0.84 N1 is equal to X N2 plus 0.97 100. And our balance using that additional information, which is that 2% that enters of CCl4, comes out the top. So 0.98 times 0.84. So since we know that 2% comes off the top, that means the other 98% of carbon tetrachloride that comes in through the feed stream is leaving through the bottom. So 98% of the carbon tetrachloride leaves through the bottom, and that's 84% of the feed stream in total. So N1 is equal to 0.97 times 100. And from there, we're able to get N1, and N1 is equal to N1 is equal to 117.83. And then since we know N1, now we can use total mass balance to get N2. So N2 is equal to N1 minus 100. So that's 117.83. minus 100. So that's 17.83 for N2. Let me put units on that. And now we know N1 and N2, so we can use the carbon tetrachloride balance to figure out X. So X is going to be equal to 0.84 N1 minus 97 over N2 N1 and we get that X is equal to 0.111. And so X is the molar percentage of X in the overhead stream. So now, we were asked for the mass and mole fractions of CCl4 in the overhead stream. So this is mole fraction. In overhead. Now we're going to do a calculation on CCl4 in the overhead stream. So Y of CCl4 is equal to 0.111. That's the mole frac. We just figured that out. And the moles of CCl4, since we want to know the molar flow rate of CCl4 in the overhead stream, we're going to multiply 0.11 by N2, which is 17.83 kilomoles per hour. And we're going to get there's 1.979 kilomoles